the weekend? My wife and I went to Roanoke to run a 5K, and it snowed during the 5K. So that was nice. Really nice and cold. I've had an interesting morning. Do you guys ever deal with like dramatic and uncommunicative people?
Yes.
And you think maybe it'll get better when you get older and into the workplace? It doesn't get better. It might get even a little worse. Oh, what a crazy morning.
Tell us what happened.
It would be unprofessional to go on, so we'll leave it at that.
Why did you bring it up?
Because I needed to vent a little. All right, so we did. Let's move on to chemistry things.
Well, obviously the chemistry in the workplace.
All right, so we did radicals. I thought we did a pretty solid job wrapping all of that up on Friday. So I'm pleased. That puts us in a good spot, I think. When's the exam?
20th.
The 20th. That is in 9 days. It's next Wednesday. Chatty. All right. So lots of office hours and things this week. I haven't got the schedule out today. There will be an office hour 2:30 to 3:30, and then all the other stuff I'll send out in an email. But again, today 2:30 to 3:30 for an office hour. That's in room 2018. All right. So today we move forward, and so we're gonna hit another one of these very canonical Ortho 1 topics today. And so. Interestingly enough, our book covers two really big topics in one chapter. I'm going to split it up quite a bit. So, chapter 9 is substitution and elimination. All right, so substitution. My goal is to definitely have all of substitution on the exam. That's exam 3. And so we'll say here, we've got exam 3 material, and then elimination. I have no idea. We'll see where we get. Certainly it'll be, we're going to cover it, but I don't know if we're going to cover it in time that I'll put it on the exam. So we'll just, we'll see what kind of time we make as we go. We shouldn't have to really be rushing at this point. I feel like by getting radicals all out of the way, we've prepared ourselves so we can spend plenty of time. We can relax a little bit, I think. We can relax a little. All right. So we'll just go ahead. I honestly, I'm doing things, I haven't even glanced at the book, so I don't know how the book does this order-wise, but I have an idea in my mind of the best way to do this stuff, and so that's, I make the rules, so that's how we're going to do it. I think it's probably better than the book. And so we're just going to start with a little intro, and so specifically, this is going to be an intro to all of this material. This is just going to give us some idea of what's going on. So we saw last class. All right, so we've learned a new reaction. We've learned that we could take something like propane, and we could treat it with a halogen, everything, I guess, except fluorine or iodine. So that pretty much leaves us chlorine and bromine. And so if we hit that with a halogen, and then of course we've got to hit it with some light as well, what we've found is we can functionalize. Now we've got two possibilities. We can add our halogen at the primary or the secondary position. What's favored? Definitely the secondary, right? So that's because that's the more stable radical, and so we would expect this to be the major product. And so what we're able to form now, directly from an alkane, is an alkyl halide. And alkyl halides are going to have a pretty prominent role in chapter 9, I would say. So we'll even go a little further and say that alkyl halides can be very useful. All right, so we're going to talk about alkyl halides quite a bit. So we're going to see that they do two main types of reactions. What do you think the reactions are?
Substitution.
Substitution, elimination, right? That's it. So let's carry this down. We'll say, now, we're going to have our alkyl halide. And so again, we'll just keep our our functionalized propane here. And so what we've got in our alkyl or our halide group is a new functional handle. We'll call it a functional group handle. And what that means is that now we've got a source of reactivity that we can play around with a little bit. We've got no longer do we just have CH bonds. We're not limited to just doing radical reactions. Now we can do some more interesting stuff that might be a little more useful. And so, like I said, there's going to be two pathways here. So one pathway we can take is going to be our substitution reaction. And so when we have a substitution reaction, we're always going to have a nucleophile. So we'll go ahead and just draw a little nucleophile there. And so what happens is exactly what it sounds like. Easy. All right, so we're going to substitute our halogen with our nucleophile. We're just going to swap them out like that. We had a halogen there, now we have a nucleophile. We've undergone a substitution, of course. We also are going to have our very sad displaced halogen over there. All right, so that's one possibility. The other possibility is going to be elimination. So elimination is kind of like the backwards reaction of something we've already learned thus far. So for one thing, we're going to have one of these. What is that?
A base.
Yeah, that's a base. All right, so we have some sort of base. And one of the complexities of this is what we're going to find is that we can take one molecule and it can be either a base or a nucleophile, right? All we have to have is a lone pair in both cases. We have to have a lone pair for it to be a nucleophile. We have to have a lone pair for it to be a base. It could be one molecule, right, with one lone pair. It could operate as both. And so that's going to be part of this chapter, is figuring out, given a molecule, well, what's it going to do? Is it going to act as a nucleophile or is it going to act as a base? And so if it acts as a base, what we're going to find is we're going to end up with an alkene. And so, of course, that means we'll also end with this thing over here. So we'll end up with HB. All right. Now, we've learned the backwards reaction here. How do we go from alkene back to our alkyl halide? We just hit that with HX, right? We do a Markovnikov addition. So basically, our elimination reaction is the reverse of our Markovnikov addition of an acid to an alkene. Now we can go the other way. We can hit our alkyl halide with a base and end up back at our alkene. So either way is going to be possible. All right, so really briefly, I've mentioned this a little bit in class, but I guess we should have it down on paper. So we're just going to say naming alkyl halides. So if we've got a fluorine in our molecule, we just treat it as a substituent. What do we call it? It's fluoro, right? If we have a chlorine, it's chloro. And we don't really give it any sort of special treatment. So basically, we are just going to treat X as any other substituent. So that means if we have, we'll just do one example. One example for fun, because we love naming. All right, so let's say we had this molecule, and we'll also maybe throw in some methyls there. Okay, so first off, we can do one of two things. We can number left to right or right to left, and we're just going to follow the rules we've already learned. We want to number such that the first encountered substituent gets the lower number. So we're going to number left to right or right to left? Definitely left to right, because that's going to allow us to give this position number 2 a substituent, right? That's a methyl, so we'll say we've got, 1, 2, 3, 4, 5, 6, 7. So just because we have our halogen over here doesn't mean we have to give our halogen the lower number. We're just going to treat it as any kind of substituent. And so what's our root name? Yeah, so this is a heptane. And then our substituents, so we've got 3 methyl groups, right? We've got 1 here and then 2 here. So that's going to be a trimethyl. And then we've got a 5-bromo. And then furthermore, we've got to figure out our stereochemistry. So let's do that. So let's see, we've got bromine would be number 1. And then this would be number 2. And this would be number 3. And so, of course, we have a hydrogen in the back. So is that R or S? R. That is most certainly R. So what we're going to have is a molecule that is 5R. And then we've got 2 possibilities. We can call it we're going to have to say 5-bromo, and we're also going to have to say 2,3,3-trimethyl. And so which would come first?
Bromo.
The bromo, right? And again, it's just alphabetical. We treat it like any substituent. So what we've got is 5R, 5-bromo, and then 2, 3, 3 trimethylheptane. All right, so it's just any substituent. You have to name stereocenters, but Pretty much it's just the rules we've already learned, so we just need to keep in mind we've got fluoro, chloro, bromo, iodo. That's the only difference. All right, yay for alkyl halides. Okay, so now that we've learned a little bit about elimination, we're going to just forget it for like a full week at least. And so we're going to focus in on substitution reactions. So now we're going to go to Roman numeral number 2. We're going to call this substitution, subtitled Intro. All right, so we've got an introduction to the chapter, but now we're really going to focus in on substitution and pretty much talk about it for a week or so. All right, so what is a substitution reaction? So by definition, a substitution reaction is going to be the exchange of one sigma bond for another sigma bond. All right, so we're going to have some sigma bond, and it's going to be broken, and in the process, we're going to form a new sigma bond, and hey, we've done a substitution. We've swapped out one thing for another. Now, substitution reactions, they have a few requirements, and so let's say that substitutions require, so first off, they require a nucleophile. Alright, so our substitutions are always going to require a nucleophile, and so we're going to draw up here just a model substitution reaction. So here's our nucleophile. It has to have a lone pair, and we'll go ahead and give it a negative charge for the heck of it. Alright, so we have a nucleophile with a lone pair and a negative charge, and so if we're going to have a nucleophile, what's it going to react with? An electrophile, and so a substitution reaction also requires an electrophile. All right, so that's kind of where our alkyl halide is going to come into play. That's our electrophile. So I'm going to say this is our alkyl halide. And it's not always an alkyl halide. We'll learn that you can use things other than halides, but that's going to be a good introduction for now. We'll talk about other stuff down the road. For now, we'll focus in on alkyl halides. And so what that's going to look like is we're going to have some mess of carbon. So we'll have an R group of some kind. And then we're going to connect it to what we call an LG. All right, and so our electrophile is pretty much all of this stuff. All right, and so in the case of an alkyl halide, our LG is going to be an X. And so we would have like methyl, some sort of methyl halide in this case. But it doesn't always have to be an X, and so we're going to start giving it this larger name of LG. And so what does LG stand for? It's the inspiration for our theme song today. All right, so John Denver's leaving on an airplane, on a jet plane. And so an LG is a leaving group. That's our third requirement. What our electrophile has to have on it is going to be a leaving group, which is exactly what it sounds like. It's something that leaves. It leaves our electrophile during the course of the reaction, and so we can see that because when we draw the product of this reaction, what we're going to find is we've created a new bond between the nucleophile and the methyl group, and then of course our leaving group has, well, it's left, right? It's left our electrophile. It's been displaced in this case. And so a leaving group, which is required, has some characteristics. And so the leaving group, for one thing, if it's going to be pushed off to be on itself, for this to be thermodynamically favorable, we're going to have some leaving group that is happy being by itself, right? In a lot of cases, it needs to be happy with a negative charge. Have we seen anything that's typically pretty happy with a negative charge? Yeah, halogens, right? Because that's why we see that something like HBr is a strong acid. It's because bromine is really, really happy out on its own. And so what we can say is that the leaving group must be stable by itself. And so along those lines, we can say that leaving groups are often conjugates of strong acids. Right? And so that's what makes the strong acid strong in the first place, is the fact that they've got a conjugate that is very, 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 very stable. And so that conjugate that is very, very stable is also going to make a very good leaving group, because it's pretty easily able to go out and be on its own. And so we can say that halogens, in general, all halogens except for what? fluorine, right? Because HF is not a strong acid. So we say halogens, except for fluorine, make great leaving groups. All right, so hooray for them. And then let's see, what we have is we initially define this thing as it's the exchange of one sigma bond for another sigma bond. And so here we can see there's the old sigma bond. And then here is the new sigma bond. So one of these breaks, one of these forms, and what we've got is a substitution. Okay, so we haven't talked anything about mechanism for this reaction. We've just talked about the starting material and we've talked about the product. So mechanism we're going to find is basically the real heavy stuff that we talk about for this section. And so let's go ahead and say mechanism. We even ask ourselves mechanism, and we'll say multiple possibilities. Yay. All right, so we've got multiple possibilities for our mechanism in a substitution reaction. And so one of these, maybe the most simple way to think about a substitution reaction, is going to be a concerted mechanism. Who remember? I know I've said concerted a few times. What is that concerted anything in chemistry?
Well, isn't the concerted mechanism when the electrophile and the nucleophile go to the atom it's reacting to at once?
Yeah, you're on the right track. It's when everything happens at the same time. So we're talking about a one-step process. We're going to form our bond, we're going to break our bond, and it's pretty much all going to happen at the same time. All right, so a concerted mechanism refers to a reaction where everything is simultaneous. All right. And so in that sort of reaction, what we're going to have is our nucleophile and our electrophile. And what we'll do is if we were supposed to draw an arrow pushing mechanism for that, well, we know that we need to form a bond between the nucleophile and the carbon. And so we'll start an arrow, of course, at the electrons. We always start arrows at electrons, right? No one's going to not do that on exam 3. And so in this case, we draw our electrophile, and if everything's going to happen at the same time in this same step, what other arrow do we need to show?
The bonds.
Yeah, and so where do we start our arrow?
Sigma bonds.
At the electrons of the sigma bond, and so those are going to snap back to our leaving group. And so in one step, what we've been able to do is form our bond and break our bond. Well, I don't know. We didn't really define our leaving group, so we'll just say Lg minus like that. All right, so that's certainly a possibility. And let's see, what else could we do? So in this case, our timing, and a lot of this is going to come down to timing, and we're going to focus on that a little bit. So if our timing is a little different, what we can have is a stepwise mechanism, which means what? Yeah, we're going to actually now use different steps, right? Stepwise. I'm not even going to define that one. I think you got it. So for a stepwise mechanism, let's see. So what are our possibilities? So let's say we go 2 steps. So let's say we have our nucleophile plus our electrophile. And so let's see what a possibility would be. We could go ahead and draw this arrow, right? And so in that case, we end up with something that looks like this. Now, how do you guys like that?
No.
I like it.
I don't like it personally.
It breaks the octet rule.
It breaks the octet rule, right? So is this going to be an actual possibility for our mechanism? No, we're not going to break the octet rule in Chem 206. Maybe in other chem classes, but not Chem 206. And so we'll say, not possible, violates octet rule. All right. And so, of course, we're doing 2 things, right? We're forming a new bond and we're breaking a bond. So instead of forming our bond first, what else could we try?
Break it first.
We can try breaking it first. And so let's see what happens when we do that. So in that case, we're just going to have our electrophile. So that's our CH3 Lg. And so if our Lg, our leaving group, leaves first, what we're going to do is end up with something that looks like this. Does that break any rules? No, it's a carbocation, right? We've seen the carbocations are certainly allowed in this world of chemistry, this crazy world. And so, in this case, what we can imagine is a two-step reaction where our leaving group first leaves to form this this carbocation. This isn't a particularly good carbocation; it's just a methyl, but we're not too worried about that right now. And so then we've got our nucleophile that's still just kind of hanging around, and so then it's obviously going to be very, very, very attracted to our carbocation, since the carbocation is electron deficient. And so in this case, again, we're going to end up with the same exact product at the end. All right, so we've got a concerted possibility, and we're going to have a stepwise possibility. And so we're going to really spend some time focusing in on the differences between these two things. The big key difference, of course, between our concerted mechanism and our stepwise mechanism is timing. And so we'll just say the only difference in mechanisms is timing. Very, very, very important key to this. Yeah?
Is there still a lone pair on the leaving group in the second step?
Yeah, it should be. Those electrons had to go somewhere. Okay. So that leads us into Roman numeral 3. That's our intro to substitution reaction. Now we're actually going to spend some time focusing in on the mechanism specifically. And we're going to learn some key details, some similarities and some differences. A good time will be had by all. All right, so Roman numeral number 3. We're going to discuss our concerted mechanism. And so our concerted mechanism, if anyone happens to have maybe seen this stuff before, it has a special name. Does anyone know the special name of a concerted type substitution reaction? And so that starts with an S. Yep, and so we have S, and then we have a little n, and a 2. And so we're going to talk about how it gets that name. That's the first thing we'll do. Why do we call it SN2? From here on out, I'm going to call this SN2. I'm going to stop calling it concerted. It's an SN2 reaction. This is the name. It's what it gets called. All right, so the first thing we're going to talk about and then I immediately call it a concerted mechanism. In an SN2 reaction is we're going to talk about kinetics, because that's where the name comes from. All right, so the kinetics of this reaction, so we're going to draw this a lot of times. We'll draw it again. So we've got our nucleophile, and so for our electrophile, we're going to use this. All right, so we'll just say, again, generic leaving group. Now, this ends up being a very good leaving group, because typically Lg is going to be an electronegative atom, and so what we've got is polarity difference that looks like that, right? It's pulling electron density away from the carbon, which means the leaving group's going to have a little partial negative, and the carbon over here is going to have a little bit of a partial positive. And that's why it's so attractive for this nucleophile to snap right into this position, is because, well, that carbon just has a partial positive. And so, of course, what we see is that our nucleophile, which of course loves partial positive charge, really any kind of positive charge, is going to snap in there. So what happens is this bond will break at the same time, and so eventually what we see is we now have our nucleophile attached to that carbon, and we've got our leaving group on its own. Sadly, it's actually a happy leaving group. That's why it's a leaving group. It's stable. Happy to do that. All right, so let's think about the kinetics of this reaction. So for this to take place, we only see one step, right? And so if we're going to determine which step is the rate determining step, well, if there's only one choice, it's the only step, right? So we go ahead and say this is our rate determining step. And so the stuff going on in this step is going to determine the kinetics. And so in this case, what we're going to have is our nucleophile and our electrophile are going to have to collide at some point, right? The only way that this reaction is going to happen is if these things bang into each other. And so that means, all right, so let's go ahead and get that down, actually. So our nucleophile and our, what is an E plus if I just, that's an electrophile, right? So that's just my shorthand for electrophile, E plus. So our nucleophile and our electrophile must collide. And so since there's two things here that have to collide, what we refer to this as is a molecular process, or a bimolecular reaction. It comes from the fact that we have two things that have to collide, come together to spit out a product. And so if we were to write a rate law for this, we could say that our rate is equal to K. What is K? Yep, it's some rate constant that we don't really care about in this class, but it exists. And so we've got some rate constant that is unique to each reaction, each individual reaction that can take place. And so then we're going to have the concentration of our nucleophile and the concentration of our electrophile. And so we can see here we've got one thing, and here we've got two things. And so from this rate law, ultimately it's the rate law that determines why we call this reaction what we do. Yeah, Alec?
Should the nucleophile be negative?
Yeah, that's fine. We're going to find that sometimes nucleophiles are negative, sometimes they're not. They're typically more nucleophilic when they're negative just because they have more charge, but it's not a necessary case. And so we end up with that name of SN2. And so ultimately the reason we call it SN2 is, all right, so S, where does that come from?
Substitution
Yeah, so we've got a substitution reaction.
of nucleophile.
Yep, and so here for N, we've got nucleophilic. And ultimately, it's just 2 that ends up being a little strange in the end. But of course, that is because we've seen it as a bimolecular process. And so that's how we arrived to that name SN2. It has to do with the kinetics of this reaction. Emily?
Sorry, can you explain the 1 and the 2 underneath?
Yeah, I'm just counting how many things we have in the rate law. How many different molecules the concentration of depends for the total rate. So.
2 electrophiles?
No, but it's just it's a total of 2 things that we're measuring the concentration of is what I'm trying. Yeah, so maybe that's a little unclear. 2 total things. All right, so that's where the 2 comes from, right? Is we've got two things in here that are going to determine what the rate is. All right, so that's the kinetics. Now we get to the even more fun stuff. All right, so for part B, we're going to talk about the stereochemistry of this reaction. And so we're going to do a little more realistic of a reaction now. So let's say we have an electrophile that looks like this. All right, so there's our halide, and then we'll put up a hydrogen on a wedge. Here we'll put a methyl. And so this group down here is actually going to be an ethyl. Okay, and so our nucleophile in this case, what we're going to use is we're going to use just SH. And so that's basically an analog of OH, right? So we have OH minus. This is just going to be SH minus. So here's our nucleophile, SH minus. It, of course, would have a negative charge, just like OH would have a negative charge. And so we've got 2 possibilities. Now we know that one of the things going on in this reaction is the alkyl halides leaving, right? And so specifically, it's being displaced. So we've got 2 possibilities for our SH. One possibility would be that, well, we're just going to come in just like that, and this we would refer to as a front side attack. Now we've already seen this. We've said that if we're ever going to do any kind of displacement, if we ever do a front side attack, we can't. Is this a displacement? It very much is. We have a nucleophile coming in and pushing something away. And so because this is a displacement, we'll say that a front side attack is not possible. So we're going to see stereospecificity in this reaction because we can never do a front side attack. SH is never going to come in from the same side that the bromine was on. That means instead of a front side attack, we must do a backside attack. And so that means we're going to come in 180 degrees from our bromine. So that's going to be the left side if we've got our bromine on the right side. And so here we've got our backside attack. It is very much necessary if we're going to do an SN2 reaction. So that's going to have stereochemical implications because once we undergo this process, well, we've lost our bromine. Now our sulfur is going to come in and it's formed a new bond with carbon. What's happened to these 3 different groups that were here already? Do you think they feel the effect of that incoming sulfur? Yeah, they definitely do, and so they're going to get pushed. Where do they get pushed? they just get pushed to the right side, right? They're going to stay on lines, wedges, and dashes that they're already on. They're just going to get pushed to the right side. And so that means that our ethyl group now ends up here. We'll have our proton up top, still on a wedge. And then we'll have our methyl on a dash right there. And so what we call this is the inversion product. Why do we call it the inversion product? Well, let's go ahead and look back here. So we've got, we name the stereocenter here. We have 1, 2, 3, and 4. And so our thumb rule says that this would be an S stereocenter, right? And so we have our thumb coming out with our group 4, the hydrogen. And so we count 1, 2, 3. So that's S. Guess what happens if we do the same thing on the right side? Yeah, so now we've got 1, 2, 3. And so we can see now with our thumb aligned with number 4, we count 1, 2, 3 with our right hand. We see that our S stereocenter has become an R stereocenter. It's the inversion product. And if we're going to do an SN2 reaction, we're only going to see one product form. It's going to be the product where everything gets pushed over and we undergo inversion. All right, mechanistically, what does this thing really look like? Actually, let me just throw in a note in here. This is a very important note. All right, so I want to make sure everyone understands that RS doesn't always change. Why is RS not always going to change? Oh.
Oh, I had a question, sorry.
You can ask your question.
What happens to the bromine? Is it over on its own now?
Yeah, it's just doing its own thing. It's been displaced, it's off on its own, it's happy on its own, so.
Josh, is it just possibility the priorities of the atoms will shift?
That's exactly right. And so in the case that we've seen right here, our leaving group was 1, and our nucleophile got assigned 1. But that's not always the case. Our nucleophile, it's not necessarily always going to be the higher priority group on our new product. It could be number 2, in which case we don't know if it's going to go from R to S. It might go from R to R just based on whatever the priority swap is. And so we'll say Y above leaving group and nucleophile are both 1, but that's not always the case. Classic exam question. I'll even tell you this is S, and then that it undergoes an SN2 reaction, and then what is this stereocenter? A lot of people will still just say, oh, that must be R, but that's not necessarily true. Yeah.
So if the stereocenter weren't to change, what would be inverted about it?
It physically, these 3 groups that are over here like this, they're still going to be pushed this way. They still have to be pushed to the opposite side. They're still undergoing. They're still undergoing inversion. It doesn't matter if the label that we give it changes. They still have to be pushed and undergo that inversion.
Okay.
And so I will say, as a rule, always reprioritize and assign our RS label. All right, that definitely trips people up. All right, so mechanistically, we've got our HS minus, we've got our substrate down here. Let's think about what kind of transition state this thing will go through. And so we know that it's going to happen at the same time, so we've got some sort of process going on like this, and so that means we're forming a bond and we're breaking a bond at the same time. And now we know these groups, this methyl, this hydrogen, and this ethyl, are being inverted. And so what we're going to end up with for a transition state is going to be basically where they're in the middle. And so our ethyl group is now going to be straight down. Our hydrogen and our methyl are going to be straight up. They're, of course, still on wedges and dashes, so we'll have hydrogen, methyl here, and so we'll show an incoming bond. All right, so we're forming our incoming bond right there, and then how do we show the leaving group leaving? Same way, right? We just used a dotted line, and so now leaving what we've got is a bromine. All right, so we can also start thinking about the developing charge, or the charge that we would have in this transition state. Importantly, if we're going to draw a transition state, what goes right here? A little double dagger, just like that, indicating that it's a transition state that we're showing inside of our brackets. Okay, so our sulfur here, it had a negative charge, and so as we're going through this process halfway through, is it still going to have a full negative charge? No, it's losing its negative charge because it's donating electrons to our carbon. And so what we show here, it's got a partial negative, right? It's on its way to being pretty much neutral. It started negative and it's going to become neutral, but in the middle it's going to have a partial negative. And likewise our bromine, it starts neutral and it's going to become negative. And so the same thing we're going to see right here. We're going to put a partial negative with our bromine. And so what we've got is basically our partial negative charge here. It's decreasing. And it's basically being replaced over here as our bromine leaves. And so what we end up with is, of course, our product that we've drawn before. So we complete our inversion plus our Br minus. All right, so that's about as detailed of a look as we'll ever see of an SN2 reaction. We see we're going to go through a transition state that ultimately is a 5-member transition state, and that's going to be pretty key. So the next thing we'll talk about is part C. We'll say structure versus rate. And if we look back at our transition state, one thing we can say is that would you imagine that, all right, so most carbons are connected, or an sp3 hybridized carbon is always connected to 4 things. How many things is it kind of connected to here? 5, right? Do you think that's more crowded or less crowded than carbon 2? It's more crowded, right? So one thing we can definitely say is that the transition state is very crowded. Bless you. And ultimately, what we're kind of seeing with our transition state is 5 bonds. We know that one's developing and one's breaking, but at one point in time, this picture right here, we do have 5 things that are at least partially connected to our carbon. And that's very, 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 very crowded. So if we're going to draw an energy diagram for this reaction, well, we know it's a 1-step reaction. So we'll have energy, reaction progression. And so we'll show this as a downhill thermodynamic reaction, because we know what happens. And so ultimately, we're going to have some energy level. We're going to start out going up, and we go back down. And so where does our transition state lie on this energy diagram? The very top. And that makes sense, right? Because that's going to be a very high energy substrate when we've got 5 things around our carbon. So this is where we find our transition. And it should also make sense because we've been talking about how transition states are always mountain peaks, right? So intermediates are valleys. How many intermediates are there in this reaction? There's none, right? We just have our starting material and we have our product. And so there's no intermediates along the way. And there's no intermediates because we only have, it's a 1-step reaction. So there's never a point in time where we hit a valve. All right, so of course, when we talk about the activation of this reaction, we say that it's the energy difference between our starting material and our transition state, or at least the highest transition state energy. And there's only one because there's only one transition state. So here we've got our activation energy, and because it's the only real increase in energy we go through, we call it the RDS. It's the rate determining step. So ultimately, the rate of this reaction is going to be determined by the difference between our starting material and our transition state right here. Let's get that down on paper. We'll say that we'll say that the stability of our transition state determines the rate of reaction. And so that stability, or the energy level, the transition state is determined by, what do you think? What do you think is going to determine the energy level of our transition state? We've already pointed out that key characteristic of it is a very crowded transition state, right? Now, can we have more crowded or less crowded substrates? Sure, right? Some substrates could have lots of hydrogens, right? That wouldn't be very crowded. Other substrates could have lots of methyls or ethyls, big bulky groups, and that would be higher in energy. So ultimately, the stability of our transition state is going to be determined by crowdedness. Is that a word?
We'll make it work.
Crowdedness. It's a word now. All right. So we're worried about crowdedness when it comes to SN2 reactions. So what we'll do is let's consider a reaction. Now let's do some comparisons. So let's say we've got our trusty S- here, and so we're going to have some form of alkyl bromide. So this is real data. So some form of alkyl bromide, and so what's going to happen is a substitution reaction where we end up with SH plus Br minus. And so what we can do is we can compare the rates of different substrates, or the rates of this reaction with different Rs. All right, so for a table, we'll say we've got our substrate, our RBr. And so what we're going to do, we'll compare methyl bromide. We will compare ethyl bromide. We'll compare this one. And then finally, we will compare a tertiary. All right, so for categories, we want to talk about types. So here, we've just got a methyl group. Here we've got a primary alkyl halide, right? And so to determine what the crowdedness is, what we're doing is we're looking at the carbon that the halogen is connected to. And so we looked at this carbon right here. We see it's connected to one methyl group, and so it's a primary carbon. And so as we work our way down, what kind of carbon is this one? Secondary. Yep, that's secondary. It's almost like I created a string. Tertiary. All right, so we've got types of carbons. So if we're going to consider crowdedness of these carbons, up top of the methyl, would you imagine that that's the least crowded or the most crowded? That's the least crowded, because we've just got little protons on there, and that's not much energy at all. However, at the bottom, when we've got a tertiary carbon, of course, that's going to be big, bulky groups that are being squeezed together, and so that's definitely going to be the most crowded. So finally, we get to our data, and we can create our final category, and that's going to be relative rates. So we can do this reaction, we can see how fast they go, and that's going to give us a good idea of what's a more stable transition state versus a less stable transition state. What do you think is going to be fastest, the methyl or the tertiary? I would expect the methyl, right? Because it's the least crowded, which means it's going to be the lowest transition state energy. And so the relative rate is about 1200 for the methyl. The primary, it slows down to about 40. So we can see there's a big difference just between the primary and the methyl there. The secondary will give the number 1. And then the tertiary, not detected, 404. Reaction, nothing. All right. So let's draw, all right, so this makes sense, right? Because if we have a tertiary, basically it's too crowded, it's too unstable, it's too high energy for this thing to even pretty much happen whatsoever. And the reason is, of course, we can draw an energy diagram that shows the energy levels. And so I'm going to create a little key here. So we'll say that this is, we'll make this one blue, this one green, and this one silver. And so the starting material and the product are pretty much going to be similar. So we'll just say all of our starting materials are here. All of our products we'll put downhill. Reaction, progression, and energy. And so our transition state is going to be the only difference between these things. What's going to be the lowest transition state energy? Methyl, primary, or secondary? Definitely methyl, right? We see it's the fastest reaction. It's the fastest because it's the least crowded. Because it's the least crowded, it's the lowest in energy. And so we'll say that we'll just draw a little hump here and say that is our methyl. And so then we'll go further up where we'd find our primary. That's going to be higher in energy. And then we can go even further up, and that's going to be our secondary. So what we find is that if we go through a methyl transition state, well, we're going to have this kind of activation energy. So it's about like this. And then if we go through the primary, we're going to have to go even higher. And so we find that the activation energy here is about like that. And then finally, for the secondary, we have to go even higher. And so depending on what kind of substitution we have, we can see that we're going to essentially change that activation energy. We're going to have very different rate determining steps. And so then for the tertiary, basically the tertiary is just off the scale. It is so high that you just don't even consider. And that pretty much, we can write that down as a rule. Tertiary alkyl halides, no SN2. Just does not happen. All right, there might be some case where someone's made it happen, but it doesn't happen in Chem 206. Just too crowded. All right, so basically that's our introduction to SN2. Yay. All right, really quickly, let's just get a little further. I know, who wants to start something with 4 minutes? I do. All right, so next we'll just talk briefly a little bit about our stepwise mechanism. This at least, we can get it on paper and then we can save some time. All right, so now we'll talk about our stepwise mechanism. And so a little preview is if our concerted mechanism is an SN2 reaction, what do you think the stepwise reaction is? SN1. Someone has seen a little bit of this before. And so we will refer to the stepwise mechanism from here on, except when I don't, as the SN1. All right, so we'll call this the SN1. And so again, we're going to do the same exact, here's the idea actually, we don't have to talk too much about this. The idea is now next time we're going to talk about the SN1. That'll probably take up 25, 30 minutes on Wednesday. And then basically the rest of Wednesday and Friday and even part of Monday, we're going to talk about all the different things that can go into these reactions. There's going to be lots of different possible reactions to consider. And so we're going to pick out 3 or 4 or 5 things like solvent, or type of nucleophile, type of leaving group, and it's going to be our job to determine, is this going to be SN2, SN1? And the big key difference is, of course, going to be the stereochemical outcome. So in an SN2 reaction, we've seen that we always get inversion product. In an SN1 reaction, we get different products. Just call it a day.
After what? I think I missed this part right here. So why was this inside a catalyst?
It's just if we're going to do a displacement reaction, meaning if we're going to form a new bond that pushes away an old bond, it's just got to come from 180 degrees. It's got to come from the opposite side, just as a rule.
With this one.
Yeah, but so what's going to happen is if we can't come in from this side, we have to come in from the opposite side. Yeah.
So you said most likely elimination will not be on the exam.
Most likely. If it is, it'll just be the tiniest bit of it.
Okay, so like if we're reading the textbook, just like make sure to read the substitution part, but don't worry about reading the elimination part.
Yeah, I wouldn't worry much about elimination at all. Like I said, if we get to it, we might have like 15 minutes to cover.
But we'll get to it after the exam.
Yeah, we'll cover the heavy part of it after.
Okay. And then workshop today, what time did you say it was?
2:30.
In that room, should we?
20.
Okay, thank you.
Hey.
When do you have time this week to meet to go over that test?
Shoot me an email.
All right.
Well, I won't remember if we talk about it.
Hey, Professor Walker.
Hey, Jared.
On the notes, just for